Hello, pre-calculus students. This is Mr. Ferris, and I'm going to walk you through lesson 1.2, which is about rate of change. So the first question has a table of smartphone sales and feature phone sales from the years 2012 to 2015. And we're going to calculate, first of all, the average rate of change between 2 years. Now, average rate of change you might recognize as slope from algebra class. That's really what average rate of change is. It's how much two things change with respect to each other. And if you were graphing this many times, if you had a line and you graphed it, it would be the slope of the line. But we're now getting into more practical applications, and so you may or may not have an actual line to calculate slope. So we just want to use really the concept of slope, which is a rate at which two things change. And so you might have remembered that sometimes we called that the change in y over the change in x. We use the Greek symbol delta to denote difference or change. So perhaps you've seen that in an algebra class. In pre-calculus, many times we're going to be taking a difference in a quantity and dividing it by a difference in time, because many times there's a quantity change over a time change. And that's exactly what we have here. We have a time change between 2015 and 2012, and we have a quantity change in smartphone sales, 1462 from 681. So that's what we're going to do on this problem. The change in the quantity would be 1462 minus 681, that's the difference in the quantities, and then the difference in the times would be 2015 minus 2012. And if you do the arithmetic there, that ends up being 781 over 3 years, and that's an average rate of change of 260 1/3 millions of smartphones per year. So on average, the number of smartphones sold goes up about 260 1/3 per year. Now, of course, it doesn't go up exactly 260 1/3 every time. That's the average of the three increases. The average of the three increases is 260 1/3 million. That's how you calculate average rate of change. It's really just the slope calculation from an algebra class, except it's done from a table. So this time, number two, if we want to do the average rate of change of the feature phones, same 3 years, so the denominator is still going to be 3, but now the difference in the sales is going to be 481 minus 1,110. And you might notice what's going to happen. Because sales have gone down, this is going to be a negative number, negative 209 2/3 if you do the computation. And that's, again, millions of feature phones per year. So now we can talk about this two different ways. We can say the change was negative 209 2/3 million, or we could say it as a decrease of 209 2/3 million feature phones per year. That would make more sense if you're just practically going to say, because you'll notice they're going down and going down and going down. So you actually should have an average decrease per year, therefore it would be a negative number. So just be ready to interpret that as a decrease. A negative rate of change is a decrease per year. Another thing we have to know for this section, they talk about increasing and decreasing functions. On what intervals would this function be increasing and what intervals would it be decreasing? Well, the first thing we have to realize is we always evaluate functions increasing and decreasing by traveling left to right. And that's kind of the common thing, I guess, in America. When we read a graph or we read what's happening over time, we usually read left to right. So imagine, you're a little ant. That's how sometimes I imagine. If you've got a little ant and the ant is crawling left to right, technically it's going to the right, but at the same time it's going to the right, it's going upward. And so the entire time the ant is traveling upward would be a time where the function is increasing. So this entire time, this function would be increasing. And we assume, I guess, that it's going forever downward. And so all the places that I just highlighted would be the places where the function is increasing. Because if you were traveling left to right on this function, you would be going up, 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 up. There was another place where the function is increasing. It would be from this minimum point all the way apparently to infinity here. So we've got two places shaded in blue where the function is increasing, and that's because as you travel left to right, the y values or the function values would be increasing the entire time. So the two places where the function is increasing would be, first of all, it starts at like negative infinity and then goes up from there. And so one interval would be negative infinity all the way to, and now we got to kind of ballpark this. It looks like about maybe 1.2, I'm going to call that. It looks like about 1.2. So the interval from negative infinity all the way to 1.2 is the interval at which this function is increasing. Now I am making an assumption that the function is traveling downward forever, and not only downward forever, but also to the left forever. It's very, very steep, so it's hard to think of this as going to the left forever, but it really is. But then when it gets to about 1.2, when x is about 1.2, that's where the function stops increasing. So there's another part of this function that is increasing, and that is from this point, which I'm going to call about 2.8. It looks like x is about 2.8. So from 2.8 to positive infinity, this function will be increasing as well. So it's basically the two blue shaded areas. It's increasing from negative infinity to 1.2, and it's increasing from positive 2.8 to infinity. Now again, we are talking about x. We are evaluating the x value, or the inputs, over which the y values or the function values are increasing. So we're talking about the x values as the domain of when the function is increasing. But then you'll notice that from this point all the way to this point, the function is decreasing, because if you were an ant and you were traveling to the right, the y values would be decreasing, 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 decreasing. So between these 2 points, the function is decreasing. So the interval over which the function is decreasing, we would say, is between when x is negative, no, I keep saying negative, I don't mean that, is when x is 1.2 to when x is 2.8. That's the interval over which the function is decreasing. So the red portion of that function is the portion where the function's decreasing, because as you go left to right, the y values are going down. And then the blue shaded regions, even though they're very, very steep, would be increasing from when x is negative infinity all the way to positive 1.2, and when x is 2.8 all the way to positive infinity. That's how we would write those. We write those as compound inequalities. That's the most concise way to write those answers. All right, we have another graph here that is kind of looks like a half of a parabola, and we want to find the rate of change between 1 and 2. First of all, between 0 and 1, between 1 and 2, and between 2 and 3. So there's 3 intervals over which we want to find the average rate of change. So the first one is from when x is 0 to when x is 1. So the average rate of change over that interval is simply going to be the change in the y values over the change in the x values. We'll just use y and x this time. So how much is y changing? Well, y started at 0, and now y is 3. So that would be 3 minus 0. The x value started at 0 and went to 1. So if we subtract right to left both times, the slope between those two, or the average rate of change between those 2 points, would simply be 3. And what that really is, on this one, you could actually kind of connect these 2 dots. And what we just calculated essentially was the slope of the segment between those 2 dots. You could think of it that way. Let me change colors, and let's do the second 2 points. The second 2 points would be from when x is 1 to when x is 2. So we do a average rate of change between those 2 points. The change in y, it looks like y is 12 for the second point, and y is maybe 3 for the first point. And then the difference in the x's is still 1. So that rate of change is going to be 9. 9 over 1, or just 9. And again, what you're essentially calculating is the slope of the line if you were to connect those 2 points. So if you calculate the slope of the line, the slope of that line would be 9. You notice it's a little steeper. In fact, it's 3 times as steep. And then for the third ordered pair, it's from 2 to 3. So we're going to be going from when x is 2 to when x is 3. So essentially, again, we're calculating, this is really hard to draw because it's almost on the curve, but we're calculating the slope of that line segment that connects the dots. Again, we're going to do delta y over delta x. The change in y looks like is maybe 27 on the tall point and 12 for the lower point. And then again, our change in x is still just 1. So it looks like the rate of change on this one is going to be 15, which is even steeper. So you might notice that going from that line segment to that line segment to that line segment, it's getting steeper and steeper and steeper. And I think you could have seen that from the curve. The curve is getting steeper and steeper and steeper. And it turns out one of the features of an increasing function, which this is, so from 0 to 3, that function is increasing. One of the features is it has a positive rate of change. So the entire interval at which it has a positive rate of change would be the interval in which the function is increasing. So we can kind of use that as one of our properties that is true for increasing functions. The rate of change has to be positive. And then if we were going to add maybe a bonus question here, I would add a bonus question here. What's the average rate of change from when x is 0 to when x is 3? What's the average rate of change? So basically we're going from the first point to the last point. So the overall rate of change from the first point to the last point would be the change in the y's. The y's were 27 down to 0, and the x's were from 3 to 0. So the average rate of change ends up being 27/3, which is 9, which is kind of interesting because it's the same rate of change as the second segment. So if you were to connect the first segment to the second segment, I said that wrong. If you connect the first dot to the third dot, the rate of change is exactly the same as from the second dot to the third dot. So those two segments would actually be parallel. So that's just an interesting little tidbit, that there's always some place where the two rates of change would be equal on a curve like that. The overall rate of change should equal one of those rates of change in there. So just summarizing, this is not a long lesson, but just summarizing the principles that we want to remember. First of all, average rate of change is simply the change in the function, whatever that function is. It could be a q function, it could just be y, over the change in x. Now the shortcut for that is delta f of x and delta x. Delta just means difference or change, and we much prefer short symbols to the words. So you'll see that a lot. And sometimes you're going to see, kind of in pre-cal, they like to do delta of some quantity compared to the delta in the time. A lot of times there's something changing over time, and so a lot of times you'll see that symbolism, but it's really the same thing. It's the change in the outputs over the change in the inputs. We also learned that the rate of change is really essentially the slope of the line segment between those 2 points. So if you have 2 points that you're finding the average rate of change, it's essentially calculating, you're actually calculating the slope of the line between those 2 points. And we drew that up above there. So hopefully that just kind of brings back some algebraic memories. And then kind of the last little bit is increasing functions as a general rule. Increasing functions, or even parts of increasing functions, are the places where there is a positive rate of change. Every place on a function where you've got a positive slope will be the place where it's increasing. Also, functions or parts of functions that are decreasing will have a negative rate of change. So if you can determine where a function has a positive slope, that's where it's going to be increasing. And if you find the place on a function where it has a negative rate of change or a negative slope, that's the interval in which it's decreasing. So those always go together, and that's actually a pretty important concept to calculus as well. So that's it. That's the lesson for today. So I will see you soon in class, and as always, make sure you bring your questions to class, and we'll try to get them answered for you.